It's our another video on function sum number. This was the manifold function. It is denoted as capital lambda and is equal to log p if n is written in the form of p to the power m, where p is a prime, otherwise it gives 0. Now that is lambda 1 is equal to log 1, since 1 can be written in the form of p to the power m. 1 to the power n is 1, and lambda 2 is equal to log 2, since and here n is 2 and 2 can be written in the form of 2 to the power 1, that is p to the power m, where p is the 2, so we can write log p, that is log 2. Lambda 6, here n can be written as 2 into 3. Here this is not in the form of, this can be written as 6 to the power 1, but 6 is not a prime, so it gives 0. Now lambda 8 is equal to log 2. This is because n is equal to 8. 8 can be written as the 2 to the power 3, and 2 is the prime and 3 is the m. Here b is the 2, so this gives log 2. Similarly, lambda 9 gives n is the 9. 9 is the 3 to the power 2, where here p is 3 and 2 is the m, so we get log p. Here some results on manifold function, that is, if for n greater than 1, log n can be written as the summation over d divides n lambda d. We can prove this by using an example, that is, let n is equal to 8, so the divisor of n are 1, 2, 4, 8. Now summation over d divides n lambda d is, it will be 1 lambda 1 plus lambda 2 lambda 4 plus lambda 8. Lambda 1 is 0, lambda 2 is log 2, lambda 4 is log 2, lambda 8 is also log 2. This gives 3 log 2, and this will be log 2 to the power 3. 3 goes to the power of 2, and this is log 8, which is log p. Here we have another result on manifold function, that is lambda n is equal to summation over d divides n mu d log n by d, and which is again written in the form of minus of summation over d divides n mu d log d. We can also show this by using by example, that is, let n is equal to n, so divisor of n are these 1, 3 and 9. Here LHS lambda n, so will be lambda 9, which is equal to lambda 3, because 9 can be written as 3 to the power 2. Here p is the 3 and 2 is m, so lambda n is equal to log p, and that is log 3. Now the RHS one, this one, gives summation over d divides n mu d log n by d. For divisor 1 divides 9, so mu 1 log n divides 9 divide 1. 9 divides 1 is 9. For d is equal to 3, mu 3 log 9 by 3, which is log 3. Log 9 by 3, log 3. And for 9, mu 9 and log 9 by 9, which is 1. Here first one is mu 1 is 1, and log 9 will be log 3 to the power 2. Okay, and here mu 3 is, it is the Mobius function. This function we discussed earlier in our previous video, and this gives minus 1. This gives minus 1, and log 3 plus log 1 is equal to 0, so log 0 into mu 9 is 0. This 2 comes come here. This is 2 log 3, and this is minus log 3. 2 log 3 minus log 3 gives log 3. So the first result, log 3 is log 3. So first result was verified. Now for our second result, that is minus of summation over d divided n mu d log d, that is minus of, here divisor of 1, 3 and 9, so mu 1 log 1 plus mu 3 log 3 plus mu9 log 9. Here mu1 is 1 and log 1 is 0, so this becomes 0. Mu3 is minus 1 log 3. Here mu9 is 0. This was Mobius function 0 into log 9, which is 0. This is minus of log 3, minus of log 3 gives log 3. So second result is also verified. Again, here an important function, that is multiplicative function. In arithmetic function, f is said to be multiplicative for f of 1 not equal to 0. F of mn is equal to f of m into f of n whenever mn is equal to 1. Whenever mn is equal to 1. Here f is the arithmetic functions and the GCD of mn will be 1. Then we can write f of m into n. F of m into n can be written as f of m into f of n. Now completely multiplicative. If here the arithmetic function f is said to be completely multiplicative if f of m into n gives f of m into f of n for all mn. Here the GCD of 1 is not required. Here the for all mn GCD which may be 1 or maybe whatever. Here if f of mn into is equal to f of m into f of n for all mn, then f is said to be completely multiplicative. Now some results on the multiplicative function, that is if f is multiplicative, then f of 1 will be 1. This can be proved by this. F of n can be written as f of n into 1. For f is multiplicative, so f of n into f of 1. Cancelling f of n on both sides, this gives 1. Here f of 1. Again, if f is multiplicative, if and only if f of p1 alpha 1 p2 alpha 2 pk alpha k is equal to f of p1 alpha 1 into f of p2 alpha 2 into f of pk alpha k. Okay. This happens if and only if f is multiplicative, or if f is multiplicative, then this happens. If f and g are multiplicative, then their Dirichlet product is multiplicative. Here the new function is Dirichlet product. And what is Dirichlet product? If f and g are the arithmetic functions, then their Dirichlet product is defined by the arithmetic function hn, which is equal to summation over d divided n f of d g of n by d, and which can be denoted as f star g. This product is known as Dirichlet product. F star g of n is equal to summation over d divides n f of d g of n by d. This product is called as Dirichlet product. And if f and g both are multiplicative, f and g both are multiplicative functions, then h is also multiplicative. Then this h is also multiplicative. Now here the another function which is Liouville function. This is the small lambda one. Here we in this video I discuss Mangold function, which is denoted as capital lambda, but this Liouville function is denoted as small lambda, and small lambda 1 is equal to 1. This is the definition. This always happen. If n is equal to p1 alpha 1 p2 alpha 2 into pk alpha k, then lambda n is equal to minus 1 to the power of alpha 1 plus alpha 2 plus alpha k. That is, for example, if n is equal to 15, then n can be written as 3 to the 1, 5 to the 1. So here lambda of n will be lambda of 15 will be p1 minus 1 to the power alpha 1 alpha 2. Here the alpha 1 is 1, alpha 2 is 1, 1 plus 1, that is minus 1 2, which gives 1. This function is called Liouville function. Now our another important function is the divisor function. The divisor function, for a real or complex number alpha, an integer n is greater than 1 and the integer n is greater than 1, the divisor function can be defined as summation over d divides n d of alpha. For example, let alpha is equal to 0 1 2 3. This can be any positive integer. on n is equal to 24, sigma 1 of 24 will be summation of d divides 24, that are these are the divisor. So 1 is the divisor of 24, so this 2 is the divisor, 3 is the divisor, 6 4 6 8 12 and 24, these are divisor. So summation over d divisors will be this sum of all the divisor. So for for n alpha is equal to 1, this function gives the sum of the divisor of any number. For alpha is equal to 1, this sigma 1 of n is the sum of divisor of n. For 2, this will give this, and for 0, this will give 1 to 0 2 0 3 0 4 6 8 12 and 24. This gives the number of divisor. And for alpha is equal to 0, this sigma 0 of n gives number of divisor of n. Now our third function, or last of in this video, this is generalized convolution. Let f be a real or complex valued function defined on positive real axis such that f of x is equal to 0 for x 0 is less than x is less than 1. Then the convolutions of alpha and f over x on x can be defined as summation over n is less than x alpha and f of s1. This is the convolution, generalized convolution. We further discuss this convolution is further we can discuss in our next videos. Thank you.